this video, I'm going to prove that an ellipse is a conic section. This is a simple proof which came from a mathematician called Dandelin in 1822. To start, I need to define what an ellipse is and what a conic section means. In everyday language, we might simply think of an ellipse as something with an oval shape, like that. In mathematics, there is a more precise definition. It is that if we imagine two fixed points on a plane, and we consider a point on the ellipse, and we draw two lines joining these two fixed points to the point on the ellipse. Then the total length of those two lines, let me call them say E and F. So E plus F must be a constant. This means that if I go to any other point on the ellipse, then the distance from those 2 points, the distances from those 2 points must add to the same answer as these two distances, and that should be true for any point on the ellipse. So this is one way to define an ellipse. So it's a very precise definition, and any curve which can be described in this way is an ellipse. Described in the sense that as long as we can find 2 points such that the total lengths of the distances from those 2 points to any point on the curve always remains the same no matter where the point on the curve moves, then that must be an ellipse. Okay. Next, so this is the one way to define an ellipse. A conic section is defined this way. Think of a cone. Alright, that should be a what is called a right circular cone, meaning that the cross section that is perpendicular to its axis is always a circle, like that, much like an ice cream cone. A conic section means that if I start with this cone and I cut this cone with a plane. So let's imagine doing it this way. So imagine a plane cutting through it. So this plane cuts a section of the cone that looks like this. And this section, the shape of this section, which is cut as a result of the plane going through the cone, this is called a conic section. So that's what this part means. And you can see that it does look quite similar to an ellipse. But there are more than one way to cut a cone with a plane. Alright, if we do it this way, as I have drawn it, you get something that looks like an ellipse. But if you imagine cutting it this way in the vertical direction, then you can imagine that the section which is cut will just keep going further and further away as the cone expands instead of closing into a loop. So that would be another kind of conic section, which I shall look at in a separate video. In this case, I shall consider the conic section that is obtained when the plane cuts at an angle like this, an angle that is enough for the plane, the other side of the plane, to come out again, so that it forms a closed curve in the section that is cut. So when we say to prove that an ellipse is a conic section, that means that we need to show that this curve, this loop here, is an ellipse. And when we say this loop is an ellipse, what we really mean is that it must be possible to find 2 points in this loop such that the distances from those 2 points to any point on the loop must always add to the same value, just like I described for this ellipse. So that's what we need to do. So in order to do this, right, before that, let me define a term. Now, I've already said this is called an ellipse. That's called a conic section. We need one more term before we go on. Now, those 2 points that I mentioned, right, that has this property, each of these points is called a focus. Right, so that's the focus of the ellipse. That's another focus of the ellipse. So in order to prove that this is a conic section, we need to be able to find 2 focuses or foci, depending on how you like to pronounce it. This is the plural for focus. So we need to find 2 such points, and we need to show that distances from those 2 points to a point on the loop will always add to the same number. So I shall describe Dandelin's method in a moment. Before that, we need a little bit of preparation, because this method requires some geometry in 3 dimensions, which is always a bit tricky. Now the main piece of geometry that we shall need is this. And let me start with a picture in 2D, a circle in 2D. So on this piece of paper, let me draw a circle. Okay, so that's just 2 dimension, just a flat circle. Now, suppose now that I draw 2 lines touching the circle. So one line goes this way, touches the circle at this point. Another line goes this way, touches the circle at this point. And those 2 lines cross at that point. All right. Now we can see from the symmetry of this picture that this length from the point of the line touching the curve to the point where the 2 lines cross, this length must be equal to this length, like that. That seems quite obvious. Right, next, let me draw a sphere. Right, so that's in 3D. That's a sphere, so that's a circle. Sphere. Suppose now that I have a line that touches the sphere at, say, this point. Okay, let's try to imagine that this is 3-dimensional. Now suppose that I have another line that touches the sphere on, say, behind it, on the other side, a point somewhere there, but on the other side of the sphere. So if I try to draw that line, alright, I use dashed line to show that this part of the line is behind the sphere, and then this part comes out so I can see. And suppose that I have this line touching the sphere somewhere behind and intersecting with this first line down here. So that is the point where it touches the sphere. Can I also say that the length of this line from the touching point to the crossing point is the same as the line from the length from the other point of contact to the crossing point? Can I say that they are equal? It is not so obvious this time. But in fact, we can. The reason is this. With these 2 lines that are crossing, I can think of a plane, the plane that contains those 2 lines. Alright, with 2 lines crossing at a point, there can only be one such plane that contains the 2 lines. So I'm going to sketch a plane like that. And now since the two lines are touching here, this plane clearly cuts through the sphere. And it would cut out a circle that looks something like this. Okay. So you see now that I have this circle which is in the plane, and I have these two lines touching the sphere and therefore also touching the circle. If I now look down from the top at this plane and the line and the circle, they would look more or less like this. And if that's the case, then clearly we know that those two lines are those two lengths are equal. So therefore, these two lengths must also be equal. So we have a 3D result now. Any two lines that touch the sphere and cross at a point, for any two lines like that, the distances from the point of contact to the point of intersection, these two distances must be equal. Okay. Now we can now carry on with the conic section to try and prove that that it has this property of an ellipse. Okay, I need to draw a cone again. That's a cone. Now this is the more tricky bit. I have this conic section here that I want to prove. Right. I need to insert two spheres into this cone. And let me start with a big sphere. Now I need to put a sphere around here. This sphere must be big enough to just to touch the sides, this curved side of the cone, and to touch the plane containing this section. So if I try to draw it, it might look something like that. So this big sphere would just touch the cone around this line. Alright, so this is the point of contact with the cone, and this point of contact forms a circle, and it would touch one point on this conic section. So that's our big sphere. Next, we need a smaller sphere that fits into this part of the cone. Now it must just touch the side, this curved side inside the cone, and it must just touch a point on this conic section, on the plane that contains this section. So let me try and draw it here. So let's say touch around here. Okay, so it touches the cone again in a circle. Alright, so this circular line is where the sphere touches the cone, the inside of the cone, and this point here is the point where the sphere touches the plane of the conic section. Now you see I have these 2 points of contact with the 2 spheres. If you look back at the definition for the ellipse, alright, you can guess that I'm probably trying to show that those 2 points are the 2 focus. Right. What next? Let me now pick a point on this conic section. Let's say I pick this point. I call it point P. Okay. Now from the tip of the cone, let me draw a line along the surface of the cone, going through this point P. Let's look at this line. Now this line crosses both this circle of contact of the small sphere of the cone and this larger circle of contact of the bigger sphere with the cone. And this means also that this line touches the big sphere at this point. Let me call this point A. Now we need a name for that point. Let me call this point F, and I'll call that point G. Now the first thing I want to show is that the length this line from F to P is equal to the length PA. Now the reason is this. You see that, remember that this point F is the point where the plane of the conic section touches the big sphere. So that means that FP, the line FP, also touches the big sphere. Therefore, the line FP is a tangent to the big sphere. And we already seen that PA just touches the big sphere, so PA is also a tangent. So these two lines are both tangents to the big sphere. In just the same way that those two lines are tangents to this sphere. And we've already seen that if these two lines just touch the sphere, then the distances from the points of contact with the sphere to the points of intersection of the two lines, those two lengths must be equal. So therefore, these two lines must be equal. Right? So FP is equal to PA because they are both tangents to the big sphere. Okay. Now, next, all right, you might be able to guess that I'm now going to try to do the same with G and the smaller sphere. So the corresponding lengths for G would be this line, GP. All right, and the corresponding line for this sphere would be, let's see, let me call that from P to the point where this line touches the sphere. That would be this point. Let me call that B. PB. So now I hope to show that GP is equal to PB, that is equal to that. So let's check. The line GP, this line GP, is on the plane of the conic section, and this plane just touches the small sphere at G. So therefore this line is a tangent to the small sphere. Now this line PB touches the sphere at B simply because the sphere touches the cone at all of this small circle. Alright, so PB is also a tangent to the small sphere. So therefore GP is equal to PB because they are both tangents to the small sphere. Okay, now let's now go back to see what we're trying to prove. We're trying to prove that distances from 2 points to a point on the curve always add to a constant. So let's look for those distances. Now P is my point on this conic curve, and F and G are the points that I hope to be the foci. So it is these two lines, it is FP plus PG. Alright, it is this sum which I hope to be a constant. But we know that FP is equal to PA and that PG is equal to PB. So therefore, FP plus PG is the same as PA plus PB. Is that a constant? Right. PA plus PB is equal to AB. Alright, now to see if this is a constant, let's think what we mean by a constant. It means that if instead of P, if I look at another point, alright, if I move P to another point on the conic section curve, then for that point, the distances from F and from G must add to the same value. Now if I'm at that point, I would expect that instead of using this line, I would now use this line. Alright, if P moves to here, then I would use this line. Okay, so if P moves to say P prime, then A moves to A prime here, and B moves to B prime. So this time, the sum of the distances from F and G would therefore be equal to A prime, B prime. But A prime, B prime is this distance. It should be the same as the distance from A to B, because the small circle and the big circle of the two spheres touching, where the two spheres touch the cone, these two circles are horizontal circles. So therefore, the distances would be the same, whether along this side of the cone or along that side. So therefore, we have just shown that this is a constant. Okay, and therefore we have proven that this conic section is an ellipse. Okay, to be precise, we have proven that to directly answer our initial goal, we have proven that an ellipse is a conic section. Okay, we'll stop here.